Compilers take the chaotic, free-text raw material of human code and force it into a structure of absolute precision and order. The engine that executes this translation is the syntax analyzer. Within syntax analysis, the LR family of bottom-up parsers represents the most mathematically rigorous and frequently tested module in compiler design. We are going to deconstruct how it works. The name LR dictates its entire mechanical approach. The L stands for scanning the input from left to right. The R means it constructs a rightmost derivation in reverse, building the syntax tree from the leaves up to the root. This animated schematic details the three core structural components of an LR parser. An input buffer feeds raw text to a central driver routine. The driver relies on a vertical stack to maintain its current state, and cross-references a massive parsing table to decide its next move. As the buffer fills, the buffer holds the string to be parsed, always terminating with a sentinel $sign. Simultaneously, the stack builds a sequential history, storing grammar symbols interleaved with specific state markers, ensuring the driver knows exactly where it is in the parsing process. The parsing table dictates every move the machine makes, but to master LR parsing, we must temporarily ignore that final table. We need to build the underlying automaton from first principles, using mathematical derivation. Human readers guess that structure using top-down intuition. An LR parser is a deterministic machine. It proves syntactic validity through mechanical, forward-moving state tracking, eliminating the need to ever backtrack. To build this state machine, we first need to define its fundamental unit of progress, the LR0 item. This equation illustrates an LR0 item. It is simply a standard grammar production, but injected with a conceptual marker, a dot, placed somewhere on the right side of the arrow. The position of this dot acts as the parser's memory. Everything to the left of the dot represents the sequence of symbols the parser has already successfully verified and pushed onto the stack. Everything remaining to the right of the dot represents the specific sequence of symbols the parser hopes to encounter next in the input stream. When the dot finally shifts to the extreme right, the parser has seen the complete production. This creates a trigger condition. The parser immediately executes a reduction, collapsing the verified sequence back into its parent non-terminal. The movement of this dot encapsulates the local logic of the machine. By tracking the dot, we track the state of the entire parser. Let's apply this to a standard expression grammar containing basic rules for expressions, terms, and factors. Looking at this animated list of grammar rules, we must first create an augmented grammar. We do this by inserting a new start symbol, E', which derives the original start symbol, E. This gives the parser a definitive single goal. When it reduces to E', it knows to halt and accept the string. We use this augmented rule to construct the very first state of the machine, state I0, utilizing an algorithm called the closure function. We place the starting item into the state box. The closure function operates on one strict rule. If a dot immediately precedes a non-terminal, like this E, the parser must anticipate encountering that symbol. Consequently, we must add all productions belonging to E into the current state. This triggers a recursive cascade. The newly added E rules have dots preceding the non-terminal, T, so the T productions spawn. Those new rules have dots preceding F, forcing the F productions to spawn as well. When the cascade halts, the closure function is complete. It mathematically mapped out every valid path the parser could take from a standstill, generating the complete set of initial possibilities for state 0. With the initial state built, the parser needs a mechanism to move to the next state. This is calculated by the goTo function. The goTo mechanic simulates the consumption of a grammar symbol. It selects all items in a state where the dot precedes a specific symbol, in this case, E. It shifts the dot one position to the right over that E, and then computes the closure of this new item, resulting in a completely new state, I1. The goTo function calculates all possible transitions, locking in the state machine's map. During actual compilation, the parser navigates this map using a continuous loop of shift and reduce actions. This three-column execution model tracks the runtime. In a shift action, the parser extracts the current token from the input stream and pushes it onto the stack. It cross-references the parsing table, finds the target state, and pushes that state number directly on top of the token. When an item's dot reaches the end of its production, the parser executes a reduce. First, it pops elements off the stack. The rule is to pop twice the length of the production body, removing both the matched symbols and their associated states. Next, the parser pushes the parent non-terminal of thy production onto the stack. It then checks the state currently exposed below it, looks up the go-to transition for the new non-terminal, and pushes the resulting state onto the peak of the stack. The division of labor is exact. Go-to calculations build the definitive map. The shift-reduce algorithm navigates that map, systematically collapsing a linear string of raw text into a verified hierarchical syntax tree. This LR0 logic works perfectly until it encounters grammatical ambiguity, exposing a critical vulnerability, the shift-reduce conflict. A conflict occurs when a single state contains both a completed item demanding a reduce and an incomplete item demanding a shift for the exact same input symbol. The determinism breaks. The automaton does not know which action to take. Simple LR or SLR provides the first defense. It resolves the conflict by only permitting a reduce action if the upcoming input token is proven to exist in the non-terminal's follow set. If the look-ahead token isn't in the follow set, the reduction is blocked. This comparison table tracks parser power. SLR relies on generalized rules, which still fail on complex languages. Canonical LR, or CLR, solves this by demanding highly specific look-ahead tokens attached directly to the items themselves, creating LR1 syntax. The consequence of CLR's precision is computational bloat. Splitting states based on specific look-ahead tokens forces the state space metric into the thousands, making it highly impractical for standard compiler deployment. Look-ahead LR, or ALR, serves as the industry standard solution. It scans the CLR map and intelligently merges any states that share identical LR0 cores. It retains the precise look-ahead rules of CLR, but drops the state count back down to manageable SLR levels. Advancing from SLR to LALR does not change the fundamental stack algorithm. It is an escalating trade-off between look-ahead precision and computational memory footprint. The interlocking mechanics of the closure and go-to functions transform abstract grammar rules into a rigid, mathematical engine. By the time the first token enters the buffer, every valid path through the language has already been mapped. We have now traced the complete transformation, converting rules into an augmented grammar, tracking geometry with the conceptual dot, and generating the automaton via transitions. Identifying a parser's specific power requires examining its items. LR0 items form the vase topology, follow sets provide the criteria for SLR, and attached look-aheads distinguish CLR and LALR. In this system, the parser never guesses. Every action, every shift, and every reduction is a pre-calculated response to the current state and the incoming input, ensuring total predictability. Mastering these mechanics provides the technical foundation for building production-grade tools. This is the exact logic used by generators like Yak and Bison to handle the complex, nested syntax of modern programming languages.